Bienvenidos, Hushamadid, and welcome UMGC learners for the CMIT-455 Section 6380 course, which is the Cisco Networking Academy's CCNP ENCOR version 8 curriculum, and this is the spring 2021 semester. In this activity, we're going to be taking another deep dive look at OSPF, and we're going to be doing this through the lens of Packet Tracer Activity 9.2.1, where we're going to look at implementing multi-area OSPF. Now, in this video, you're not only going to learn about multi-area OSPF, we're going to be talking about the Type 3 LSA, which is the summary LSA in OSPF, but we're going to be taking a look at the page out of the John T. Moy book that I believe, with respect to this topic, multi-area OSPF, is the most important page in his book. And again, I'll show you the book that I'm referring to when we get there. So here's the activity we're working with, 9.2.1. You can see we have area 0, we have area 1 over to our left in pink, and area 2 over to our right here in purple. And so we're going to perform some configuration work, and then we're going to be answering some very important questions. So we have our addressing table, as we normally do, and let's go ahead and take a look at the instructions. So we're going to configure OSPFv2 on router 1. And so here's router 1 right here. And again, if I go back to the addressing table, you can see that they've kindly indicated in which area each interface on each of the routers is to be a member. And so we need to keep that in mind, because it's not going to be as simple as simply saying network and then putting our network statement in and then area 0. We're going to have to pay attention as to which area we place the interfaces in. Now, a quick note. One of the first questions learners ask is, why would I do multiple areas? And there are a whole host of reasons as to why you would do that. Now, the original premise behind multi-area OSPF and the reason that John T. Moy implemented multiple areas was for scalability with the routing protocol. If you think back to when OSPF was created in the late 80s, you had very slow circuits. And if you had one big area 0 and your routers were in Alaska, California, Florida, let's say Texas, New York, and Maryland, and you had an incident, an interface went up or went down, and you had to wait for the Link State Database in that area to synchronize, you might be waiting quite some time, again, on legacy circuits. And all of those messages that need to go back and forth, right? That link state update, the link state acts, things like that, that took time. And they found that it just didn't scale. And so they needed some sort of approach to deal with that fact. And multi-area OSPF addressed that reason. Now, multi-area OSPF also provides abstraction. And so the example that I just gave you of an incident in, let's say, a nationwide or continent-wide big area 0, and all the routers are in the same area and we're running over really slow circuits, if you have an event happen, remember the link state database needs to be identical on all of the routers in a given area. And so for that to be true, we have to wait for things to synchronize. Well, if we break up area 0 into smaller non-area 0 areas, like area 1 and area 2, we can limit or constrain the failure domain. And here's what I mean by that. If we have a failure over here somewhere in area 1, yes, area 1 is going to be impacted, and we're going to have link state updates and link state acknowledgements, and we're going to need to have the link state database fully synchronized here. But the update that goes into area 0 is not going to force area 0 to fully reconverge. And when I say reconverge, I'm talking about the running of the shortest path first algorithm, because that's really what's happening when changes are being made. Remember, the SPF algorithm is what is creating that graph, right? That tree for us that each of the routers will look at to determine what is my shortest path to get from me to some other destination. And this is what multi-area OSPF is allowing to happen, and it's doing it through abstraction. Again, we're talking about multi-area OSPF. And we're also going to talk about the fact that MOI on that page simply states that they looked at distance vector routing protocols in order to arrive at this solution to the problem that they were having, which is the scalability, the isolation of the failure domain, and the use of multiple OSPF areas. Because as you're going to see in this video, when you have multi-area OSPF, you are going to have distance vector routing protocol behavior that takes place between area 0 and the other areas. And what I mean by that is it's that abstraction. Now, make no mistake, I'm not saying that OSPF is a distance vector routing protocol. That would be crazy, because it is not. It is a link state routing protocol. It will always be a link state routing protocol. However, when we're doing multi-area OSPF, it is still a link state routing protocol, but it will behave and act in distance vector ways. And we'll talk about that. Remember, distance vector routing is referred to as routing by rumor. And that's a phrase I wish they would have used in the text. I haven't seen it in the ENCOR text. They used another analogy, like I think it was a signpost. But remember, with distance vector routing protocols, and we'll simply draw some lines out here, if we're running EIGRP, right, and this is router 1 and router 2 and router 3 and router 4, when running EIGRP, router 1 has no idea what is going on over here at router 4, or that router 4 exists. It has no idea about router 3, or that router 3 exists, or any of the networks behind any of these routers. All router 1 knows about is what router 2 is telling him. In other words, it's up to router 2 to communicate to router 1 everything that's going on over here. And this is classic distance vector behavior. Routing by rumor. Router 1 is routing based on the rumors it's hearing from router 2. And those rumors are, hey, if you need to get to this network over here behind router 3, just come to me. If you need to get to this network segment behind router 4, just simply, hey, router 1, come to me, router 2. Router 1 has no concept that there is a router 3 or that there is a router 4. In a distance vector behavior and in a distance vector routing protocol, it's routing by rumor. And the same is true over here. Router 4 has no clue that there's a router 2 or a router 1. It simply knows that I'm directly connected to router 3, and router 3 is whispering in my ear, hey, if you want to get to this network, which I know how to get to, it's over here, just come to me and I'll get the traffic there for you. That is routing by rumor. And that is what we're going to see between the areas. And it's the type 3 summary LSA that makes that all possible. Now, one of the first things that will confuse learners is when they hear summary LSA, they think, oh, you mean like IP address summarization. No, we're talking about a summary of the area. And so it's going to pass along information that represents the summarization of the networks in the area, but it's not summarizing those networks in the classic sense of, oh, if I have 192.168.0.0/24 and then 192.168.1.0/24, and can I collapse all of this down by doing the bitwise operation here and figuring out that we have a /23, which is going to be the 192.168.0.0/23, which would encompass both of those networks. And again, this is sort of classic IP address summarization. That is not what is happening between the areas. It is a representation of all of the networks in the area, but it's not giving you all of the OSPF information. It's giving you a summary of that OSPF information represented by the network IDs, right? All right, well, let's dive into this activity here, and those are important points to cover before we dive in. So we're going to jump on to router 1, and let's give ourselves a little bit more room with which to work here. And so here we are on router 1. It says configure OSPFv2 on router 1 with the process ID of 1, and there's that router ID of the all ones. So we're going to go from user exec to privilege exec with the enable command. I'm going to go into global config. We're going to say router OSPF1. That is our process ID. It does not need to match between routers in OSPF. I talked about the I shouldn't say the corner case. I talked about the use case where you may want to have that match, and that would be in an MPLS layer 3 VPN scenario where OSPF is the PE to CE routing protocol. Again, outside of our scope of this video, but keep that in mind. There is a use case where you would want process IDs to match. This is not one of those use cases. All right, so the first thing we're going to do is set the router ID to 1.1.1.1. Now, it's not talking about doing any passive interface work here, so we're going to leave that on the table. So we're not going to touch any of the passive interfaces. And so I'm checking to see if it wants the network command, and I'm assuming that it's going to. All right, so we're going to go ahead with the network command. We'll see if we get the points, because there is another way to do it. We could go under each of the individual interfaces, and let's take a look at those interfaces. Do show IP interface brief, and I could say IP OSPF, the process ID number, 1, and then area, and the area number to which I want that interface to belong. So on router 1, we're going to say network, because I believe that they're going to be grading this, and we'll find out very quickly here. Network, and it's going to be 10.1.1.0. And again, I'm putting the network ID in. I'm not going to put the exact IP with quad zeros here for the wildcard mask, because I don't believe they're going to give you the points for that. So I'll do it as they would want to see it done here. So network 10.1.1.10, and it's going to be a /24 wildcard mask. Now, you'll notice here that it says area 1. So on router 1, and we'll assume that this top interface is gig 00, this interface will be in area 1. Now, by definition, a router, an OSPF router that has an interface in area 0 and at least one interface in a non-area 0 area, i.e. area 1, area 2, area 51, area whatever, something other than 0, this by definition is an area border router, an ASBR. I'm sorry, ABR, area border router. I was thinking to myself when I was going to introduce the ASBR, but it's an ABR. So by definition, it has an interface in area 0 and at least one interface in another non-area 0 area. That is your area border router. All right, so we're going to say area 1. And we did get a lot of points for that, so this is exactly how they want to see it. So now we've got gig 01, and that is also going to be in area 1, but the network ID, and I was not anticipating that to happen, the network ID for the network statement is going to be 10.1.2.0, and it's a /24, and that is the other gigabit interface on this router that goes to sort of this innocuous cloud over here, this area 0, right? And you'll notice that we have a neighbor over there. And we can see that neighbor, and we can probably guess that it might be router 9 based off that router ID. So we'll put that interface in area 1. And then finally, and actually, let's wait a second here, and let's run some validation commands. And let's see what we have before we've got too much going on. So you can see it's probably router 9 and router 5. If I say show IP OSPF neighbor, you can see here that router 9 on this segment here, the top segment, again, we're going to assume that's, in fact, let me see if we can get, okay, so the top segment's gig 01. So the bottom is gig 00. So we can assume here that out the gig 00 interface, that bottom connection, that the router is router 9, and that is the router ID. And the top link, gig 01, goes to router 5. Let's take a look at our link state database. Show IP OSPF, database. And what do we see here? And this is something that did not come up yesterday in the video. And again, hindsight's 2020. I was showing you some different examples, and we never talked about the type 2 LSA, which we get an opportunity to talk about here. So this is area 1, and here is my database. Again, you can see router 1 is in area 1. It's about to be in area 0 as well, but right now it's only in area 1. And so here's what I see. Remember, the type 1 LSAs will be generated by every OSPF speaking router in that area. Type 1 LSAs and type 2 LSAs do not cross area boundaries. And as you move on in your studies with OSPF, this is probably one of the more complicated concepts that learners will run into. So again, in an area, we're going to have type 1 LSAs. Every router will generate a type 1 LSA. The type 2 LSA is only generated by your designated router, the DR. This is what the type 2 LSA is explaining. Here is the IP address to the designated router, router 9, for the segment that router 1 is connected to. Remember, think of these two connections here as mutually exclusive in the sense of designated router election, because each segment in OSPF will have its own designated router elected. So in other words, it's not a designated router per area in this scenario, right? Now, if I had two routers connected, if we only had area 0, I want to make sure I clarify that statement. If this is area 0 and I've got two routers connected here, then yes, in all of area 0, one of these is going to be the DR and one is going to be the BDR. But typically, we have more connections in the area, right? And what I'm saying is, it's on each of these segments where a DR-BDR election would take place that you will have a DR for every single one of these segments. And a BDR, again, because we've got two routers on every one of these segments, so you would have a DR and a BDR, and it might not be that this router here is the DR for this segment and this segment and this segment. It could be the DR for one of the segments here and the backup designated router for that segment and that segment. So again, these are things that will come into play. What I'm saying over here is, again, we have two mutually exclusive Ethernet physical connections that are dealt with as individual segments. And the type 2 LSA generated by the DR tells the router to which it's connected on that segment, hey, here is the IP address of the designated router. That is the function of the type 2 LSA. On the top connection, which I believe is the gig 01 here for router 5 that we're connected to, here is the IP address for the designated router. And that's the information that the type 2, the network LSA. This is our type 2 LSA. Here is my type 1 LSA. These two LSA types do not transit the area boundary. In other words, router 9's type 1 LSA that router 1 has describing all of router 1's links is not going to be flooded into area 0 and then subsequently then flooded out over here to area 2. And if you follow that statement, right, what I'm saying is I'm describing to you what Moy was dealing with. How do we break the area up into smaller, more manageable chunks that will allow OSPF to scale? Because if a link over on router 9, and again, let's just say that guy right there is router 9. If this network segment, that link goes down, do I want a flooding of LSAs to come into area 0 and then another in the same LSAs to be flooded out over here so that area 2 knows what's going on in area 1, and if we had another area over here that this ABR sends information out? No, that defeats the purpose of multi-area OSPF. Remember, think of it as limiting the size and scope of your failure domain. Because a failure over here on router 9, and that segment right there goes down, the shortest path first algorithm will not fully run over here. There will not be a reconvergence event in area 2. There will not be a reconvergence event in area 3. There would not be a reconvergence event in this area, area 4. It's going to be limited here to this area. And then there will be a single, right? There will be a type 3 LSA that describes a summarization of this area from a network perspective. But again, it's not summarizing the IPs that make up this network. And you'll see that here when we take a look at the type 3 LSA. So let me clear the screen. Hopefully that made sense, right? And that is what the multiple areas are preventing, is type 1 and type 2 LSAs having to be flooded into all of the other areas. Oops, sorry, I just knocked over my tablet drawing pen there. So that's what multiple areas facilitate, right? Is inside of the area, we've got all these type 1s, and that's automatic. You're going to get a type 1 LSA for every router because that's how it's defining and describing its links to the other routers in the area. And then if and only if in that area you have a DR-BDR election, because we have a broadcast network type here. Remember, is there going to be a DR-BDR election here? No, this is a point-to-point network type. What about over on this segment? Will we have a DR-BDR election between router 2 and the area border routers? No, because these are point-to-point network types. This is a serial point-to-point link. You will not have a DR-BDR election there, right? So remember that. All right, so let's clear the screen, and before we get logged off, let's step back over here, and that is my link state database. And that's what it looks like for area 1. I've got my type 1 LSAs. I've got my type 2 LSAs because we have designated routers that are involved in area 1 that router 1 is connected to and sees, right? And this is, again, we're from router 1's perspective here. Now, the last interface on router 1, let's get into global config. Let's go, and I should say, let's go into router OSPF1. And what we're going to say here is network, and this is going to be the network between router 1 and router 2. So we're going to say network, and that is a 192.168.10.0. And you can see they give us the network ID right here along with the subnet mask. And we know that a /30 means that the first 30 of 32 bits have been used to represent network bits, meaning I've only got 2 host bits left. And so that would be a 255, 255, 255, 252 in dotted decimal notation. The inverse of that, meaning if I subtracted that number, 255.255.255.252, from the all 255s, meaning 4 octets with 255, I would get 0.0.0.3. That is my wildcard mask here. And this interface is in area 0. Now, I don't know if we're configuring router 2 here. We'll see what happens. Yeah, we're going to configure. So you're not going to see anything happen here for right now because we haven't configured router 2. Now, let's go ahead and say show IP OSPF interfaces. Now, I can't say interface brief, unfortunately. I wish they would add that in here. But what I can see is take a look. Gig 00 is up. The network type is broadcast. My OSPF cost, right? We haven't talked a lot about layer 3 traffic engineering with OSPF or path manipulation. You can also see here, my state on that link, I'm the BDR. This is router 1, right? We've already seen that it sees router 9 on its segment over the gig 01 and router 5 over its segment, which is the top one, gig 00. It sees those as the DR and it tells us right here. So that show IP OSPF interface command is a really nice command. And it's even nicer when you can tack on the brief keyword at the end of it. Now, here on the serial interface, it is a point-to-point network type because it is a serial interface. There are only 2 things on either end. It is point-to-point, nobody else in between, right? On a broadcast, multi-access network type, like Ethernet, which is what these connections are, we might have a switch in here. We don't know. There could be a switch in there. Who knows? So you could have other devices. And that's why you have that DR-BDR election taking place. All right. So that's router 1. Now let's take a look at, we did that. I'm sorry, I'm going to have to leave that addressing table up so I can see what's going on here. So now we're on step number 3, configure OSPFv2, which implies IPv4. Remember, OSPFv2 implies IPv4, has nothing to do with IPv6. For IPv6, you've got different RFCs. It was a complete rewrite of the OSPF routing protocol and it's OSPF v3. And then you have OSPF v3 with address families, which is another RFC. And we'll get to those in turn. So on router number 2, let's go ahead and configure OSPF. We'll go from user exec as indicated by the greater than sign to privilege exec indicated by the pound or the hash sign. Let's get into global config router OSPF and let me double check to make sure we're okay here with repeat the above steps. Okay, so we're going to do router OSPF1. We're going to say router ID, right? The fingerprint for router 2 in area 0 is going to be 2.2.2.2. And now I'm going to issue the network statements here that are going to be required. Now, I'm first going to go ahead and do the network statement for area 0 out here, right? And you'll see if I click on this, you'll see these are locked. There's no way for us to get in there. And that's kind of part of the activity because we're going to be asked to provide information about what might be going on out here, right? And who might we be connected to? And are they the DR? Are we the DR? So we're going to say network, and this is the gig 00, and it's 10.2.1.0, and it's a /24, the easiest of the wildcard masks to calculate, /24. And it is area, okay, everybody here is in area 0. So all the interfaces on router 2 are in area 0. That makes router 2, you'll sometimes hear it referred to as an internal router because all of its interfaces are in the same area. Now, you might also hear it referred to as a backbone router. Remember, area 0 is considered the backbone. And give some thought, and I'll give you the answer later. Why is it that area 1 and area 2, and if we had an area 3 up here and an area 4 over here, why is it that they all have to attach to area 0? Why do all non-area 0 areas traffic have to pass through area 0? In other words, I can't directly connect area 1 and area 2 together here. I can't directly connect area 1 and if we had an area 3 up here. You can't directly connect them. They all have to be connected to the backbone area, area 0. Think about why that might be the case. What is the purpose of that? And I'll work through the rest of this activity here. So that's going to be area 0. And then we're going to say network 192.168. And now here's where we're going to see some activity. 10.0.0.0.0.3, and you can see we're connected with presumably router 4 based off that router ID, which we've seen multiple times. Now, though, what you're going to see is now we're going to see type 3 LSAs. As soon as I hit enter here, we are going to be establishing our adjacency with router 1, the area border router, because it borders area 0 and area 1. It sits on the border. Now, this adjacency is going to come in there. It came up rather quickly. Let me say, do show IP route OSPF. OSPF. Let's see what we have in our routing table here. And this is it right here. So, O represents an OSPF learned route. In fact, let me just say do show IP route so you can see the, excuse me, the legend here for the codes. O is an OSPF learned route. If you have OIA, it means it's an OSPF inter area route, a route learned from another area. And that is what we're seeing with these two advertisements right here. And OIAs, right, we are learning these through a type 3 LSA. Well, how would I see that? Well, remember, do show IP OSPF database, right? Remember, this is going to show router 2's link state database. And here I'm proving to you, do you see the type 1 and type 2's from area 1? Where are those? Remember, type 1 and type 2 LSAs do not transit area boundaries. That would defeat the purpose of having multiple areas. So here's my type 1 router LSAs. Here are my type 2 network LSAs, because remember, out this broadcast network type link, gig 00, I'm connected to router 4. And who do I see router 4 as? Do show IP OSPF neighbor. You got it. Router 4 is the DR on this multi-access segment, the broadcast network type that segment is on. And so I see router 4 as my DR. And that's why the priority, remember, on the interface, IP OSPF priority value, the default is 1 on broadcast network type segments, multi-access segments. On point-to-point segments between router 2 and router 1, we have the dash here again. The priority is 0, meaning we don't need a DR or a BDR. We don't need a DR or a BDR because it is a point-to-point network type. There's only 2 routers involved here, 1 on each end of the segment. So we don't have a DR. So this proves that the type 1s and type 2s that we see here on router 2, these have nothing to do. Am I seeing the type 1 for router 9 and router 5? No. I don't see the type 1 from router 5. I don't see the type 1 for router 9 in area 1, because type 1 LSAs and type 2 LSAs do not transit area borders. That would defeat the purpose. And again, I only see one type 2 coming from the DR on that link right there into this cloud over here. So let's now go ahead and say, I'm sorry, I've got it right there. I was going to say show IP OSPF database. So we've got these new guys right here, right? Summary net link states that I'm seeing here in area 0. And these should look rather familiar to you. 10.1.1.0 and 10.1.2.0, and I'm up here right now. And router 1 has those interfaces right here, right? Because those are the two networks that router 1 is connected to. It doesn't appear on router 1 anyway, and let me take a look here real quick. So it doesn't look like router 5 and router 9 show IP route OSPF. Yeah, so the only route that I'm learning is the 10.1.2.1, which is, again, remember, it doesn't, and this becomes confusing for learners. Why do you not see an OIA on router 1 for this segment up here? Why is it not a type 3 on router 1? Because it's from area 0. Yeah, exactly. Remember, router 1 is straddling the fence. Router 1 is in area 0. So it will see that route for that network up next to router 2, the 10.2.1.0/24. It will see that as an O, an intra, not inter, an intra area route within the same area, because router 1 has an interface. So router 1 is like, yeah, I'm in area 0. So I'm going to see that as an intra area route, not an inter area route. However, on router 2, when we said do show IP route OSPF, router 2 says, you know, I don't have an interface over here into area 0. And so these LSAs that came into area 0 from area 1, these are representing I shouldn't watch, I'll be careful here. I was going to say external, but when we say external, that leads to ASBR, Autonomous System Boundary Routers. And we would be talking about non-OSPF routing domain information. So I'm going to avoid the term external. So router 2 is saying these are inter-area. These are coming from another area. That, me as router 2, I don't have an interface into that area. And that's the area border router takes the type 1 LSAs and regenerates those and packages them into a type 3 LSA and sends that into area 0. And router 2 sees that and says, oh, okay, it's a type 3, meaning it's coming from this other area that, you know, I don't know anything about. Router 2 doesn't see router 5 and router 9. And so what is it that's happening right here? The ABR. And what is the behavior right now? Router 2 is getting routes for area 1 over here, but has no clue what router 9 and router 5 are doing. It doesn't even see them. All it sees is this advertisement via a type 3 LSA, a summary of the area from a network perspective of what's over here. This is distance vector behavior. Again, let me be clear, because I don't want you to walk away thinking, oh, OSPF is a hybrid routing protocol, and it's distance vector and it's link state. No. OSPF is a link state routing protocol. Full stop. Period. Punto final, right? OSPF is a link state routing protocol. It will always be a link state routing protocol. However, when you are using multiple areas, it behaves just like a distance vector routing protocol, does it not? Because router 2 has no map of what's going on over here. All router 2 knows about area 1 is, hey, I've just received from this router 1 is telling me that if I need to get to the 10110 or the 10120, that I need to come to router 1 to get there. That is distance vector behavior. Plain and simple, distance vector behavior. And so this is a good segue over to the John T. Moy, and again, what I like to refer to as the most important page in the blue book. Remember, it's not the yellow book. The yellow book that Moy published is if you would like to create in a programming language like C your own OSPF implementation. That is not what the blue book is about. Page 55 here talks about hierarchical abstraction. And it's all about, in order to build large OSPF networks, we allowed an OSPF routing domain to be split into regions or areas. That is why. This was the original reason behind it. Details of any particular area were to be hidden from all other areas. And that is exactly what's happening here. That's what we're seeing happen. Router 2 doesn't know about routers 5 and 9. All it gets is the type 3 summary LSA that says, if you'd like to get to these two networks, come to me, the ABR. I'm your broker. I'm the area border router. I can get you to these two routers. You don't need to know what's going on behind me that I'm going to need to do to get there. Just send your traffic for those networks to me. That's what's going to happen. And so that's why, and I'll scroll up a little slowly here, you get down to these last two paragraphs. And this is what it's all about, and specifically the penultimate paragraph. Although we were using distance vector mechanisms between areas, we wanted to avoid the common pitfalls of distance vector algorithms. So we required that all areas be directly connected to a special area, the backbone area, by forcing all of an area's routing information, meaning a non-area zeros routing information, area 1, 2, 51, 99, to go through the backbone area on the way to other areas. It's a hub and spoke area organization that standard distance vector mechanisms could handle without problems. And so, in other words, it's to avoid loops. That is what the backbone area is all about. It's about avoiding looping that can happen. And so in order to provide a loop-free way to do this multiple area setup, all non-area zero areas must transit through the backbone area. Now, you're looking at that last paragraph and you're saying, well, wait a second. I don't think that's necessarily true. What about virtual links? And we will get to virtual links in turn. For right now, remember, all non-area zero areas must connect to area 0 through an ABR. Now, just like everything, is there a way for me to weasel around that requirement? And it's going to be the virtual link. And we'll talk about virtual links in turn. But this, to me, is the most important page in that blue book when you go to explain and fully understand the design decisions that were being made at that time when OSPF was being created and the challenges that Moy was facing and how they addressed them. And this is not the only occasion where Moy borrowed how distance vector behaves in order to implement multiple areas in OSPF to allow it to scale. He also borrowed the idea of the designated router. And that idea was borrowed from a routing protocol, which is still in use today. And I mean, it is pervasive in service provider environments. And that routing protocol is intermediate system to intermediate system. And again, I love looking at the history and the decisions and why those decisions were made, because it gives you a better understanding as to why things are the way they are. All right. So let's now transition back here. And we left off on router 2 looking at the type 3 LSA. So now let me say do show IP OSPF database. And of course, we don't have context sensitive help. So remember, if I said do show IP OSPF database router, that would show me all the type 1 LSAs that router 2 sees. If I wanted to see the type 2 LSAs, I could say network. If I want to see the type 3 LSAs, I say summary. And take a look here. And this is, I'm going to give full screen, or not full screen, but as much as I can so we get everything on one screen here. So here it is. Show IP OSPF database summary. So here are the 2 type 3 LSAs that came from where? Who advertised those LSAs? Yeah, router 1. There's that fingerprint. There's that router ID. That is not an IP address on router 1. That is the router ID for router 1. And so router 2 is saying, and so this is what router 2 is seeing. He's seeing this type 3 summary LSA coming from router 1. And what is it summarizing? Again, it's not a summarization of a set of IPv4 addresses. This is the summary network number. So here is the network number. And you can see we've got the network mask down here. And so that if I want to get to that network, and you can see the network masks or the subnet mask is right up here. So if I'm trying to get to some address in the 10.110/24 address space, router 2 has learned a route via a type 3 LSA from router 1 that tells router 2, hey, you don't need to know everything going on over here in router 1, or in area 1. There's your abstraction. That's the abstraction that Moy is talking about right here on your screen. You don't need to know what router 9 sees or where this advertisement's coming from or anything else going on over in area 1. Here is a network and a subnet mask length. If you're trying to get to an address in this network, come to me. I'll take care of it from there. That is abstraction. That is hierarchical abstraction. That is distance vector behavior right there at its finest. And so that's really a point that I like to drive home, because that is really a true understanding of what multi-area OSPF is all about. Okay. So those are do you see they got the 2 type 3 LSAs right here. All right, so let me clear the screen and let's drop router 2 back down a skosh. And there we go. And so we completed the configuration on router 2. Now let's step over to router 3 and let's take care of the configuration on router 3. So we're going to go from user exec to privilege exec into global config, router OSPF1, router ID 3.3.3.3. And then we need network statements. So we need one for the first gig 00 link, 192.168.2.0 and a /24. Again, always the easiest wildcard masks to sort out. And that's going to be in area 2. And then we've got 192.168.1. There we go. And we'll make that known there. And so we had one adjacency come up, and then there's the other one. And so you can see the routers that are hidden here in these different areas in the clouds that we're looking at. We've got router 4, router 5, router 6, router 7, and router 9. I haven't seen a router 8 yet. So we've got 2 routers over here in area 2, 2 routers over here in area 1, and 1 router, router 4, up here in area 0. All right, now I need my final, final network statement for the 192.168.10.4 and 000.3. And remember, that is not an area 2 connection because router 3 is an area border router. It has one interface in area 0 and at least one interface in a non-area 0 area, i.e. area 2. Now, could they have moved router 3 up a little bit here to show it kind of straddling the area 0? Like it, you see router 1 here kind of touches both. Yeah, they could probably moved it up, but not a big deal because now we understand exactly what an ABR is and what the ABR's purpose and function is. So let's drop that network statement in, and that is going to, let me pull up, get to the questions here. That is going to pull up an adjacency here, establish an adjacency between router 3 and router 2, although on router 2, did I actually put in show run section router OSPF? I'm thinking I had left off a statement, and I did, because we should have seen it before then. So router OSPF1, and we need a network statement in there for the 192.168.10.4, and now we will see on router 3 here, within a few seconds, an adjacency pop up, and there it is. And who's my new neighbor? My new neighbor is router 2. So let's go ahead, let's save our configurations here across the board and make sure that we don't lose anything just in case. Remember, Packet Tracer is software, and software can and does crash from time to time. So back to router 3, if I say show IP OSPF neighbor, that's what I would expect to see. I see that router 6 and router 7, those are for their respective segments. They are the DR. And again, if I was to say show IP OSPF interface, I could see who the BDR is for that segment, probably me. Show IP OSPF interfaces. And so who is the backup designated router? In both cases, I am the backup designated router. Now, the bottom neighbor, router 2, priority is 0. Why is that? Yes, because it is a point-to-point network type. By default, priority is 0, meaning I don't want to play silly DR and BDR games because I am a point-to-point network type. I don't need to do that. And that is why we see the dash out here, because there's not a DR, there's not a BDR, and there's not going to be one. So we put a dash out here to indicate that. So now let's go ahead, and we're right here on part 2, and we're going to answer every single one of these questions. And as we're going to go ahead and start, let's go ahead and start with just question number 1 here. So which routers are internal routers? Now, the definition of the internal router is a router where all of the router interfaces are in the same area. And so if we take a look at our diagram here, we can see that routers 5 and 9 over here in area 1, these would be considered internal routers because they have all of their interfaces in area 1. If we were to look at router 2 and router 4, they have all of their interfaces in area 0. So not only are router 2 and router 4, you could consider those internal routers, they are also backbone routers because all of their interfaces are in the backbone area. And so we also have right here, and let me pull that back up, routers 6 and 7 in area 2. Those are internal routers. So which are the internal routers? We can say 5 and 9 and 6 and 7, and we can also piggyback 2 and 4 on there, keeping in mind that 2 and 4 are backbone routers. Those are routers with all of their interfaces in the backbone area. And now let's talk about question number 3. Which routers are area border routers? And the area border routers are kind of obvious here. From looking at our diagram, we can tell that the ABRs are the router 1 and router 3 nodes that are in our diagram because they are on the border, router 1 of area 1 and area 0, and router 3 is on the border of area 2 and area 0. So that's the first 3 questions. Now, which routers are autonomous system routers? Now, when you're reading this, I don't believe what they're asking you for here is autonomous system boundary or border routers, ASBRs, because they ask about ASBRs further down here. So my reading of that question is which routers are in the OSPF routing domain, the OSPF autonomous system. And it would be all routers, 1 through 9. Again, keeping in mind that there is no router 8, at least we don't see a router 8 in here. So 1, 2, 3, 4, 5, 6, 7, 9, those would be our autonomous system routers. Now, remember what I just said. Autonomous system boundary router or autonomous system border router. Those two terms are synonymous with each other, and we're going to be expanding on those here shortly. Now, which routers are generating the type 1 LSA? And again, remember, this is what the OSPF shortest path first algorithm, Dijkstra's algorithm, is all about in terms of constructing the graph of the network. It's dependent upon those type 1 LSAs. Again, if we come to router 2 and I say show IP OSPF database, remember, this is the link state database for router 2. And as such, we have some specific values in here that are referred to as router link states. This is your type 1 LSA that router 2 sees in the environment. This is the LSA that describes all of the links that router 2 sees, his type 1 LSA, and then the type 1 LSAs that router 2 is receiving also have link information in them to describe the links that those routers have. And so it's the type 1 LSA. It's the first one listed here. It's the router LSA. And the link ID is your router ID. And that's why it's important to have some sort of naming, some sort of router ID configuration standard that you're using that's well known, that everybody can recognize right away. Because you can see if you just had a bunch of random IPs in here with 2 or 3 routers, maybe not a big idea. If you've got 20 or 30 routers and you're trying to look at the link state database, and these are just random IPs that are being pulled off interfaces or loopbacks or whatever the case may be, that's going to be a difficult ask. The advertising router is also the router ID. Now remember, this is how OSPF, the dynamic routing protocol, is finding the routers that are in the graph. It's based on that fingerprint, that unique social security number if you're in the States. It's all about the router ID. And so the answer to the question is every router generates a type 1 LSA because, again, it is the type 1 LSA. If I was to say show IP OSPF database router, here are the type 1 LSAs that router 2 sees. And you can see who the advertising router is. So router 3 says, hey, I've got a link connected to another router, a point-to-point link. Hey, I'm connected to a stub network, the 192.168.4.10, right? And so you can see all of the links that are represented in each of the type 1 LSAs, and this is the link state database on router 2. And router 1 and router 3 will also have identical link state databases. That is a requirement with OSPF. Now, Are there ways that you could get in here and filter routes out within the same area? Yes, that is something you would never want to do because you will end up with unexpected results, and it would probably end up with, if this is your production network, as a resume generating event, as I like to call them. So remember that the type 1 LSA has that link information. Now, which routers are generating the type 2 LSA? Well, what is the type 2 LSA? First of all, we have to know what that type 2 LSA is all about. So do we have any type 2s? The network LSA. And we do. And what exactly are these values here? Well, remember, the type 2 LSA is all about the DR-BDR election that's going to take place, and you're going to end up with a designated router when that election takes place on multi-access broadcast network types like Ethernet. So router 2 has a serial connection here and a serial connection here. Let me ask you, who's the DR going to be on this transit segment? Exactly. There is no DR-BDR election that will take place, or I should say the DR election, and then ultimately the BDR will be whoever's not going to be the DR, given that you've got two routers there. So on a point-to-point network type, there is no DR-BDR election. It's not required because remember, the DR and the BDR are all there to provide scalability on multi-access network segments so that not all routers become fully adjacent with each other when you have three, or I should say when you have more than three routers. Because with four routers, at least two of those routers are going to come into the two-way state and be DR other or druther. So they see each other on the multi-access segment, but they're only fully adjacent with the DR and the BDR, not with each other. And so the type 2 LSA is all about the designated router. In fact, the link ID in the link state database is not the router ID. That is the IP address of the designated router. This is the router ID of the designated router. And so the type 2 LSA advertises to whom everybody participating in this broadcast multi-access network type would become fully adjacent and would send their updates to. And so that's your type 2 network link state advertisement. And so the question, which routers are generating type 2 LSAs? Well, it's only the DRs. And that's an easy thing to figure out with the show IP OSPF neighbor command. And we can clearly see that router 9 is generating a type 2 LSA. Router 5 is generating a type 2 LSA. So you see it here, and you could also see it by saying show IP OSPF, and I thought we had database on here, show IP OSPF database. And if I do a question mark, take a look at that. I can say, show me only the type 3 LSAs, the summaries. Show me only the type 1 LSAs, the routers. Or show me only the network LSAs, the type 2 LSAs. Now, external and ASBR summary, we will be getting to those shortly, and those are good ones. So, router 1, if we were to scroll back up a little bit here, and I think that's where it starts, in area 0, because remember, router 1 has an interface in area 0. So it will see the type 2 advertisement from router 4. Because remember, type 1s and type 2s, and I'll kind of draw it off here to the side, type 1 and type 2 LSAs are bound in the area in which they occur, meaning the type 1 LSA is not flooded from area 0, is not flooded into a non-area 0 area. That would defeat the purpose of multi-area OSPF. Because remember, if I'm flooding the type 1 LSA everywhere with the link link advertisement, right, in the link configuration in that type 1 LSA, then do I need multi-area OSPF? No, I don't, right? So the problem then becomes, then we've got this huge single area. And in a geographic use case, say that this is in Siberia, this is in South Africa, and this is in Buenos Aires. So would you want this to all be in one massive area? No, the use case for this is you have your backbone area, and then you have these satellite spoke areas, area 1 and area 2, so that if there is something that happens, like on this router right here, let's say there's a network segment here in area 2 in South Africa, and that goes down. If that happens, there is going to be LSA activity. And there's a possibility of a full run of the shortest path first algorithm, but only in area 2. And so by using multi-area OSPF and by segmenting the areas geographically, we are also limiting the size and the scope of the failure domain. And we'll define the failure domain as the domain in which, for OSPF, again, we're talking about OSPF, in which OSPF would have to do a full recomputation of the shortest path tree using Dijkstra's shortest path first algorithm. Because that's the last thing you want to have happen is down here in South Africa, in the middle of nowhere, you've got a link that goes down, and then we have a flap link. If it could just be flapping, right? That is going to generate LSA activity. But is it going to generate a full recomputation of the SPF over here, or the SPT over here, the shortest path tree? No. Because the type 1 and type 2 LSA information is bounded by the area border routers, right? And so that's where the area border routers come into play. And that's kind of a nice segue here into question 7. But first, let's wrap this up. Who are the routers generating the type 2 LSAs? Well, on router 1, if I say show IP OSPF database network, I can see router 4 is advertising a type 2. I can see router 5 is advertising a type 2, and router 9 is advertising a type 2. In fact, why don't we say this, include advertising. Whoops, and show IP OSPF database network, and it doesn't like the pipe there, and it should allow me to do that. Oh, I'm sorry. I think, what did I say? Yeah, I said include. It should be include advertising. Thought I might have misspelled something. Okay, so it doesn't like that. On real iOS, we can get away with running this command, right? Show IP OSPF database network pipe to include advertising, so that all I see are those lines right there. The 3 lines that I would be looking for that will tell me which routers are advertising type 2 LSAs. And again, that is the quickest way to figure that out. From router 1's perspective, I'd have to come up here to router 2, and how many type 2 LSAs do you believe? And actually, the answer's right there. So I say show IP OSPF database network. We see 1, right? And that proves that the type 2 LSAs from area 1 and the type 2 LSAs we're going to see over here in area 2 are not flooded into area 0, because router 2, which is in area 0, even though it's directly connected to router 1 and router 3, will not see the type 1 LSAs or the type 2 LSAs from either area 1 or area 2. Those LSA types are bound to the area in which they are originated. And therefore, the only router advertising a type 2 LSA here is router 4. And again, it makes sense, right? Because I think router 2 is the BDR, router 4 is the DR, and there it is, a broadcast network type, multi-access medium like Ethernet, show IP OSPF interface. And there's your gig 00 right there. And there's router 4, and it is the designated router. And that is why router 2 sees the type 2 LSA from router 4 and nobody else's. It doesn't see router 5 and router 9. It doesn't see router 6 or router 7. It only sees router 4 because the other type 2s are occurring and being generated or flooded, if you will, in these other areas. And they're bound to those other areas. And so then you may be asking, well, if the type 1 LSA is bound to area 2 and the type 1 LSA is bound to area 0 and you can't flood the type 1 into area 0 from these other non-area 0 areas, then how does area 0 learn about the networks and the reachability information? How does it learn that reachability information to all of these networks that are over here? And that's what takes place at the ABR. That's where the magic is, at the area border router, at least the magic in this context, which is this network reachability information, the 10120/24, the 10110/24, and then these two networks, the 192.168s, those are learned in area 0 via type 3 LSAs. And here's how that works. The type 1 LSA shows up here on router 3 from, let's say, for both of these, router 6 and 7 here, router 5 and 9 here, hits the ABR, and the ABR says, hey, there's network information in there. There are links that are in there. I'm going to generate a type 3 LSA. And I'm going to generate that type 3 LSA because it's an inter-area LSA. In other words, coming from another area. And this is one way OSPF is able to determine the trustworthiness of routing information. And think of it like this. An intra-area route, INTRA, is the most trustworthy. And so we'll give it a score of 10. Again, that's not a metric. I'm just trying to give it a score. We'll say, hey, that's super trustworthy. 10 is the highest you can get. Because if the routing information has originated within my area and it is intra-area routing information, it doesn't get any more trustworthy than that in terms of the LSA types. And then you have inter-area routing information. And inter-area routing information is a step down. So we'll just say we'll drop it by 2 and make it an 8, right? And so this is our highest trustworthiness. Inter-area, because it's not from my area, but it is from another OSPF area, is still pretty trustworthy, but not as trustworthy as intra-area routing information. So intra-area would be the type 1 LSA information that I'm learning. Inter-area is the type 3 information that I would be learning coming from other areas represented by the summary LSA type 3. Now remember, we're not talking about summary, and you'll see that that is not what's happening when we look at the database. We do not take those two IP addresses and perform a bitwise summary on them to come up with a single network advertisement, and then that is what is given to area 0. Now, can we summarize with OSPF? We can, but that is not the function of the type 3 LSA. The type 3 LSA is the summary LSA, and we're on router 2 here, and let's say show IP OSPF database. Let's look at the summary net link states that are seen in area 0. So in other words, let me see from router 2's perspective all of the type 3 LSA routing information, the inter-area routes that have come from other areas via the type 3 LSA. And these are the 10.1.2. And so there you see it. There are area 1's 2 networks, and here are area 2's 2 networks. And you can see that these are not summarized. Those are the network IDs. Let's dig deeper. Show IP OSPF database summary. What do we see? And let's just dump all of it out here, and we'll scoot back up to the top. We're going to have, again, 4 entries here. Here is the advertising router. And so this is how Routers in area 0 know how to get to this network. Again, remember, they're looking for the router ID, and then they're going to find that router ID in their shortest path tree, in their graph. And the reason that they have the router ID for router 1, you might be looking at that and saying, well, wait a minute. Router 1 is in area 1. How come there's a type 1 LSA in area 0? It's because there's an interface on router 1 in area 0. It's an area border router. So it generates a type 1 here, and it has a database for area 0. And that same database, it has a database in the link state database. There's a link state database for area 1. It has a link state database that is reflective of both areas to which it's connected. And in fact, you'll see that here in just a second, but let's take a step back here. So here's the link state ID. It's the summary network number. But remember, it's not talking about summarizing multiple /24s into a 23 or into a 22 or into any other summary. It's the summary of the network information that's over here. Because think about it. This is all the information that's being given to area 0, which area 0 will then send over here to area 2. It's the only information that we're getting about area 1. Let me ask you this. Let's go back to router 2. Does router 2 see, show IP OSPF database, where are the type 1 LSAs for routers 5 and 9 and 6 and 7? 5 and 9 are in area 1. Router 1 has no clue that there's a router 5 and a router 9. And same over here behind router 3. Router 2 has no idea that there's a router 6 and a router 7. And so now we come to the discussion that we previously had about OSPF and when it starts to behave like a distance vector routing protocol. A routing protocol that is routing by rumor. In other words, router 1 is spreading rumors in area 0 that if you want to get to these two network segments over here, just come to me. And router 3 is also spreading rumors into area 0. And again, from area 2, it'll come into area 0. It'll make its way over to area 1. But right now, think of it like this. Router 1 and router 3 are spreading rumors into area 0 about network reachability information behind the area border router. But are they giving me anything else? Do I know anything else? No. All I know from router 2's perspective is here's some reachability information. Here are some networks that if you come to router 1, you can get to these two guys. If you come to router 3, you can get to these two guys. That is distance vector routing behavior right there at its finest. And we talked about the EIGRP configuration where I strung, I think, 4 or 5 routers together. In EIGRP, I only know what my neighbor is telling me. And that is exactly what is happening here. Now, to be clear, OSPF is a link state routing protocol. It was originally a link state routing protocol. It is a link state routing protocol today, and it will always be a link state routing protocol. What I'm saying is it behaves and shows characteristics in a multi-area OSPF configuration of a distance vector routing protocol. And if we were to step back to the PDF that we had open earlier, you saw where it said in the penultimate paragraph where Moy basically admits that in order to solve the problem of scalability with OSPF and to be able to break up larger single areas that were simply just crashing because there was just so much link state database information, LSAs going back and forth, it was bananas. In order to solve that problem, he looked at distance vector routing protocols and said, yeah, okay, well, let's create an LSA type to do that. And that's your type 3 LSA. That's why they went with this convention. And that's exactly why it behaves like a distance vector routing protocol. And so these are very interesting things and things to understand. Remember, I gave you a geographical use case where you would put, one central area 0 and then all these satellite offices. Remember, OSPF, multi-area OSPF, think of it like a hub and spoke. And that also explains why we have all areas that are non-area 0 areas having to attach to the backbone area, area 0. It's to prevent loops as well. And that's the hub and spoke configuration. So area 2 can't talk directly to area 1. Like we don't have them connected up together here. Think of it as a hub, area 0, the backbone area, and then my spokes, all of my non-area 0 areas. So it's the type 3 LSAs. So which routers are generating my type 3 LSAs? Well, that is very easy to see from router 2's perspective. The advertising router, here's the router ID, and this is how in the shortest path tree, OSPF knows if the traffic hits router 2 and it's trying to get to the 10120 or the 10110, who's the advertising router? And then I figure that out in my shortest path tree. How do I get to router 1? How do I get to the fingerprint that is router 1, that router ID that we assigned to router 1? This is how the nodes are identified in the graph, which is the shortest path tree. It's all through the router ID. And that's why the router ID is such a critical, the most critical component when you're configuring OSPF, because it's by that value that the router will be known throughout the area, right? Throughout the area. Because again, routers 5 and 9 and 6 and 7, if we could get onto those routers, they have no clue that there's this network over here behind router 2 and that there's a router 4. All they're going to know is that they have seen a type 3 LSA, which would have been the information for this network that hit here and would come out this way as a type 3 advertisement. And the same thing to these guys here, it would be an inter-area. Again, it's routing information from outside their area. So who's generating the type 3 LSAs? It's our area border routers, router 1 and router 3. And we've conclusively been able to show that that's exactly what's happening by saying show IP OSPF database and show IP OSPF database summary when we only want to see the type 3 LSAs. All right, so now we're going to get into the good stuff. Which routers, and this is sort of the trick question here, which routers are generating the type 4 and type 5 LSAs? Well, if you look at question number 10, why would there usually be an ASBR in this type of network? Well, let me ask you, do we have any ASBRs in this network? We don't. We have internal routers. We have area border routers. We have backbone routers, which are also internal to area 0. But again, they're typically called backbone so that it signifies them as being only in the backbone area. And so there are no ASBRs. And so we're going to answer question 9, and then we're going to tackle 8 and 10 at the same time. So question 9, again, I think question 9 should have been question 8, followed by question 8 is number 9. So we get the type 4s and the type 5s and the ASBRs one right after each other. So how many inter-area routes does each router have? Well, that's, again, low-hanging fruit. All we have to do, show IP route, is look at the routing table. How do we tell if it's an inter-area OSPF route? Is it an OIA? So how many inter-area routes does router 1 see? It sees 2. Router 3 should also see only 2. Show IP route. And there they are. But how many inter-area routes is router 2 going to see? Show IP route. It's going to see 4. It's going to see the 2 over here. I didn't mean to go over the cloud there. So it's going to see these 2 networks here, which are in area 1, and it's going to see these two networks here, which are in area 2. So now my question to you is, why don't router 1 and why don't router 3 see an OIA network, an inter-area network for the 10.2.1.0/24? Why is that not the case? Why is it that it's an O? It's an intra-area route and not an OIA. Exactly. Router 1 and router 3, and this is where inter-area OSPF can get a little tricky. Router 1 and router 3 have interfaces in area 0. So when they learn about the 10.2.1.0/24, they learn about it as an intra-area OSPF route. Remember, if it's intra-area, it's just the O, right? Meaning they learned about it from an area in which they have an interface. Now, if we could get on to 6 and 7, if we could get on to routers 5 and 9, we would see that they are going to see that network as an as an OIA type 3 LSA. And that's really, in the routing table, we see OIA, and what that means, that indicates it's a type 3 inter-area route. So remember that. That's why 1 and 3 don't see that as an inter-area route. They see it as an intra-area route. All right, so that takes care of number 9. So we had 2 inner areas here, 2 inner areas here, and 4 inner areas on router 2. So now we want to address question 8 and question 10. So the question that 8 is asking, which routers are generating type 4 and type 5 LSAs? Well, there are no routers generating the type 4 or the type 5 LSA. And there's a very good reason for that. The type 4 and type 5 LSAs, respectively, are for external routing information, meaning routing information coming from outside the OSPF routing domain. Now, remember, I'm not saying from another area. That would be inter-area. I'm saying routing information coming from maybe, I don't know, over here, and we've just got this router here, which is my edge router connected to the ISP. This is not routing information from inside my OSPF domain that might be advertised in here. That would be via the type 5 LSA. And I would need to, in most cases, redistribute that information into OSPF. The same could be true down here. Again, the ASBR, the Autonomous System Boundary or Border Router, this would be the ASBR because it is on the boundary between my OSPF routing domain and some other non-OSPF routing domain. And so the ASBR deals with external information, not intra-area information, not inter-area information, but external information. Now, it doesn't have to be only in area 0. I could have off of router 1 here a network connection, an interface dedicated to a connection here with an EIGRP router that is also redistributing information into area 1. And then for reachability, it would be, vice versa. We could redistribute OSPF into EIGRP and EIGRP into OSPF. But the idea being is that routing information that I'm redistributing in from EIGRP is coming from outside, external to the OSPF routing domain. And the same thing is true over here. If I've got this other connection and we've got a RIP, I'll spell that out so it doesn't look like a router. We've got a RIP network over here, and we're redistributing the RIP information into OSPF and OSPF into RIP. this would be, the RIP information would be external. In both cases, we are dealing with type 5 LSAs, and these ABRs right here are now both ABRs and ASBRs, because not only do they have one interface into area 0 and at least one interface into another non-area 0 area, they have an interface to an external source of routing information that we are using to redistribute into OSPF. And so they would also be considered, or could be considered, area border routers, again, depending on how we're doing the configuration here. But type 5 LSAs, that is the external routing information. And again, you saw it when we looked at the diagram here. You can see the, where is it at? Did I go right by it? The type 5, here it is, OSPF external type 2. Now you'll notice that there's a type 1 and a type 2, and I'm going to touch on this because we're going to configure this, because I'm about ready to turn router 2 into an autonomous system boundary router. And how would I do that? Well, here's how I would do that. I would go into global config. I would say, sorry, not router OSPF5. I would say interface loopback 99. And you can see the interface comes up. Loopback interfaces are always up unless we shut them down. And I'm going to give it an IP address of 99, 99, 99, 99. We're going to make it a /32. So all 255s, all 32 bits. It's a host route, right? Now, you'll notice I'm not going to put IP OSPF1 area 0 here. I'm not going to add a network statement. So if I come to router 1 and I say show IP route, there's no 99 network. If I come over here to router 3 and say show IP route, there's no 99 network. And the reason for that is that the interface exists, but I haven't originated an LSA advertising that, hey, if you're trying to get to the 99 network, you would come to router 2, because we're not going to originate it into OSPF. We're not using OSPF to do it. It's a directly connected interface, right? So if I say do show IP route, you can see here's the 99. It is directly connected. That's how loopback addresses are seen on routers. They are seen as directly connected interfaces. Again, they're virtual, but they're seen as if they were directly connected. So the example I gave you before, where we could have type 5 information if we redistributed information from some other protocol. Well, it just so happens in the context of talking about redistributing directly connected, we can imagine that as being a routing protocol. Now, it's not a dynamic routing protocol. There's no RFC for directly connected, and there is no router directly connected one that you set up. But in this context, we're taking external routing information from a directly connected source, from the directly connected interface we've created, and we are going to redistribute that into OSPF. And here's how you would do that. I would say router OSPF1, and then I'm going to say redistribute connected. Now there's a few things we're going to talk about here, and I'm going to demo all of the settings that you're looking at right now. And the first one is the metric. So I can set the metric, right? But we're not going to do that. We're going to let the default play out so that we can have that conversation. The metric type. Remember I said there's the OE1 and the OE2? Well, here's where we're going to see how we could set the metric type if we didn't want it to be an OE2, which is the default. The most important option is the subnets option, because I'm going to hit enter right now without putting a tag on there, without putting the subnets or the metric type or the metric setting, right? And that's the message you're going to get on older iOSs. Now, this is a 15.1-ish simulator here. And so when you see this message, only classful networks will be redistributed. What that means is that networks that OSPF will redistribute must align along their classful boundary in terms of subnet mask. Let me give you an example. If I had, let's say it wasn't 99.99.99.99. Let's say it was 192.168.50.5. If the subnet mask on that was not a /24, OSPF is not going to advertise it. If it's a 172.16.39.52, if the subnet mask is not 255.255.00 class B, OSPF without that subnet's keyword is not going to advertise it. And I'm proving that to you right now. Let's come back to router 1 and let's see, where's that 99 network? I just redistributed it into OSPF. Why is it not showing up? And it's because we didn't use the subnet's keyword, because a 99 would be a class A address. And we don't see the class A subnet mask on that loopback interface. I used a /32. We subnetted the daylights out of it, right? We used up every single possible host bit, right? And the same thing is true here. Show IP route. Where's the 99 network? It's not going to be on router 3, and it's not going to be OSPF learned on either router 3 or router 1 or any other router, because we redistributed it and we didn't use the subnets keyword. So let's rerun that command. And the reason I say newer iOS is you don't have to use the subnets argument is because I've seen on the newer iOS where it will automagically add that keyword to the command you're running. Now, I'm not a fan of that. I almost like the fact that I have to type it in. I've got to remember to type it in because I've always done it. Even on the newer iOSs, I don't leave it to chance that the iOS is somehow looking out for my best interests, right? You want to take control of everything you can when you're configuring things. So always, if you have subnets that do not align with a subnet mask for the classful boundary for that network, you need that keyword. So now let's hit enter. Now let's go over here to router 1. And now we will see, as soon as OSPF, there we go. I went a little too quick between the routers. And here we go. There is our OE2. The administrative distance for OSPF is 110. The metric, the cost that router 3 sees to reach that network is 20. Remember, when redistributing into OSPF, that is the default LSA type. That's the default route type. It's a type 5 OE2, and it's the E2 is the default type, not the E1. That is the administrative distance for OSPF, and that metric is 20. And here's the thing with the defaults. They work, right? And they work great. But that metric of 20 never changes for that route. It will always be 20. So if you had to go 40 routers down the line and you said show IP route, you would see this type 5 LSA and it would have a metric of 20. Now, maybe you have a better way of getting there and you don't want it to just simply show 20, right? Because again, it's never going to change. Now, it's not a bad thing in this case, because if you look at this, Area 1 and Area 2 have how many ways to get up here to Router 2? They each have one. There's only one way out of Area 1, and that's through Router 1. And there's only one way out of Area 2, and that's Router 3. So in this use case, this is not a big deal. Now, in more complex configurations, where the cost of going through maybe slower links or faster links is going to be a concern, that is where you use the type 1 metric, the metric type of 1 to get an OE1. So let's go back to Router 2, because we're going to change this on the fly. And you're going to see the cost should be 80 something, I think 84. But let's rerun the command. So redistribute connected, and I can't do subnets first. We've got to say metric type. And here you go. Do I want it to be an external type 1 or an external type 2, an OE1 or an OE2? OE2 is the default. I'm concerned about the actual cost. I want the metric for all redistributed routes to be reflective of what the actual cost is going to be. Not that silly 20, right? That doesn't help me at all. So I'm going to say metric type 1. And again, we still need to put the subnets keyword in there. So we give it a second. My guess is we've got LSA update that's going to take place here. And we're going to say show IP route and give it a second. It will flip from an OE2 to an OE1. And there it is. And it is 84. Okay, good. So you can see an OE1 external route says my administrative distance is still 110. OSPF, whether external, internal, inner area, intra area, the administrative distance is 110. But with this external route, I want to know the real cost. And I want that to be added up through the hops that I would need to get to so that I have an accurate reflection of what it actually costs. And if you need that, the OE1 is the metric type that you want to use. So now let's take a look at our link state database. Let's say show IP OSPF database, and remember, external. So I can look at just the externally learned information. And this is convenient, right? Very easy to see here because we've got a single type 5 autonomous system external link state. Your OE, in this case, 1, that's what that 1 represents right there. It's not a cost of 1. Excuse me. It's not a cost of 1. It's the metric type of 1. And so we can see here, here's the link state ID. This is the external network number. It's a /32, 99, 99, 99, 99. Now, here's what's interesting. The advertising router, which is where the redistribution took place, is on router 2. And from router 1's perspective, who has an interface in area 0 and who sees the type 2 LSA, the type 1 LSAs for router 2, or I should say router 2's type 1 LSA, it knows exactly how to get to router 2. And remember, router 2 is the advertising router. And this type 5 LSA, when it shows up here on the area border router, goes out as a type 5 LSA to routers 5 and 9. And so router 5 and router 9 are going to see OE1 routes that would have different metrics. It wouldn't be 84. It's going to be more than that because you have to take into account the cost of the links and the segments it's got to pass through to get from router 5 and router 9 up to router 2. So we get a cumulative cost with an OE1. More importantly, in that type 5 LSA, this is what they're going to see for the advertising router. And that is a problem. Because do router 5 and router 9 know what the router ID for router 2 is? They don't. And why don't they know that information? It's because they don't get the type 1 LSA. They get a type 3 summary LSA over here, because these are internal area 1 routers. They don't have any type 1 or type 2 LSA visibility into area 0. So they're going to get this type 5 LSA saying, hey, if you need to get to the 99 network, just go to router 2. And they're going to say, router 2? Or I should say, go to 2.2.2.2. And they're going to say, well, that's funny, because when I say show IP OSPF database on router 5 and router 9 and router 6 and router 7, who are internal non-area 0 routers, They don't have anything for router 2 in their link state database because they don't see the type 1 LSA generated by router 2. And so that's a problem. And it's a problem that is solved by the type 4 LSA. And so all of this was kind of the run-up to talk about the type 4 LSA. So let's get on to router 1. I'm sorry, we're on router 1. And the reason I didn't say show IP OSPF database and hit enter before I ran that external command is I wanted to show you this. Now let me show you this. For area 1, take a look at what we have here for area 1. What do you see? You see summary autonomous system boundary link states. These are your type 4 LSAs. And these type 4 LSAs that are advertised by router 5, advertised by router 9, advertised by router 1, what does the type 4 LSA identify here? It identifies the advertising node of the type 5 LSA. The type 4 LSA provides the reachability information from an OSPF perspective as to how to get to the 2.2.2.2. Because you can see here, they're going to learn that type 5 LSA. The advertising router is going to show us 2222. The type 4 helps them. Think of it as like a summary of what's going on over here for this external information. So whereas the type 3 LSA is a summary between areas in OSPF, the type 4 LSA is sort of a little helper guide summary for how you get to the autonomous system boundary router to get out of the OSPF domain to get to this external routing information. Let's take a closer look and say ASBR summary. And specifically, we'll look at this one right here. And you can see who's the router that's advertising that. It's the 1111. What's the link state ID for the ASBR? It's the 2222. And the problem with that is that router 5 and 9 don't have a type 1 LSA and don't know how to get there. If I come over to router 3, show IP OSPF database, and we come down, we see the same thing. Here's your type 4 LSA, right? And again, it's a helper. Show IP OSPF database ASBR summary. Go to the bottom here. And the advertising router of that type 4 LSA is router 3, who's telling people, hey, if you're trying to get to the 2222, you can come to me. I know how to get there to the ASBR because I am getting the type, I have the type 1 LSA. That's how I know how to get there in that shortest path tree, in the graph that the shortest path first Dijkstra's algorithm calculates and puts together. And so that's the service, that's the function and the purpose of the type 4 LSA. So if you don't have external information, you don't have any type 5s. If you don't have type 5s, you don't have type 4s. The type 4 and type 5 LSAs are inextricably linked. Type 1 LSAs don't need type 4s to help out. Type 2s don't need type 4s. Type 3s don't need type 4s. Type 7s don't need type 4s, right? It's the type 5 that needs the type 4. And so that's the answer to number 8. And why would there usually be an ASBR in this network? We talked about 3 different reasons. One reason may be that you have an EIGRP domain here. Maybe you've got a connected network you need to advertise into OSPF of a router 3, right? Or maybe you're connected, excuse me, to the internet for router 2. And so the final command, let's say show IP protocols, right? And what do we see here with the show IP protocols? We see that we're running OSPF, we see our router ID, and lo and behold, what does that say? It's an autonomous system boundary router because it knows that it's an ASBR because it's generating type 5 LSAs. And we are redistributing external routes from what protocol? Again, talking about its routing protocol, connected. Number of areas in this router is 1. We are only in area 0. No stub networks, no not so stubby networks. Again, when you get into more advanced in the ENASRI course, you're going to start talking about stub networks, the different types of stub. Stub, totally stub, not so stubby, totally not so stubby. And what else are we interested in here? The administrative distance, and there it is, 110. And we see type 1 LSAs, right? Routing information sources for router 1, router 2, router 3, and router 4. Those are who we're getting the type 1 LSAs for. There's no router 5, no router 6, no router 7, no router 9. Now, if I was to say show IP, show IP OSPF is another good one that they don't have over here. And the reason that that's a good one is that you can see that it's in the area backbone. And again, it points out that it is an autonomous system boundary router. And it's also serving the function at, router 2 is not an APR. So it's serving the purpose of being an autonomous system boundary router. And that's where we can see that in 2 places. Show IP protocols, show IP OSPF. And then we see some things down here where there's no authentication being used, right? That's a problem. So I think we have hammered this activity thoroughly into the ground in terms of coverage of all of the different information that we wanted to talk about. Now, I've already mentioned the MOI Blue book, which is the book to buy. There's a yellow MOI book. Do not buy the yellow book. That is a book if you want to write your own implementation of OSPF in like the C programming language. So the blue book, The Anatomy of a Routing Protocol, that is definitely the book to get. Let me pull this up here. And there's another source, the RFC. We talked about this, RFC 2328, the MOI book on OSPF. And then if you were to Google Cisco OSPF Configuration Guide, you can actually download the entire OSPF book on configuration. And this is an amazing source of information on how to configure OSPF on Cisco routers. And with the exception of the book, the RFC and this document are 100% free. And I'm going to get on my soapbox here for a second. If you're going to be a network engineer and this is going to be your craft and this is going to be your trade, you need to know OSPF. You need to know OSPF because it is the predominant interior gateway routing protocol in use today. No question. Yes, EIGRP is used, but it is not used as much as OSPF is. And there are a multitude of reasons for that. OSPF is not proprietary. Now, you might be thinking, no, stop, wait. There's an RFC that talks about EIGRP. It's RFC 7868. Donnie Savage wrote it, and so did Don. I can't remember Don's last name all of a sudden. Not Don Slice. Or is it? Yeah, Donnie Savage and maybe it is Don Slice. Anyway, so the EIGRP Brain Trust, right? And Donnie Savage, who I've actually had the honor of meeting multiple times and talking to multiple times about EIGRP, there's a very important EIGRP feature that is not detailed in that RFC. And it's one that allows EIGRP to scale. And it is the stub network feature. So yes, there is a description of how you would create your own, and we can actually look at it right here, RFC 7868, and we'll see that is your EIGRP RFC. It is Don Slice. Yeah, so for some reason there, I couldn't remember his last name. And then you've got Peter Paluk, who is a genius. I've also met Peter multiple times. absolutely brilliant Russ White router god. So these are guys, and you can see Donnie Savage's name is up here. He has been maintaining EIGRP and has rewritten every line of code in EIGRP at least once, he said. And he's been maintaining it since, I think, 93, 92, 93. So Donnie Savage is not someone who is not, he is the subject matter expert on EIGRP. He is the primary source for information. And he is, as you can see here, the top author listed here. So this is the description of how you would go about creating your own implementation of EIGRP. But let me search here for stub. Gee, that's funny. EIGRP has a stub feature, but as I search this entire document, all however many pages long this is, there's no stub feature that comes up. And that is not part of this implementation. And in speaking with Donnie at Cisco Live, and this was a number of years ago in Orlando, he had said that they wanted to see what the level of adoption would be before they rolled the stub feature explanations out there. Again, the history of why EIGRP was Cisco proprietary for a very long time has to do with the fact that Donnie and the team at Cisco took it to the IEEE or the IETF to propose it as a distance vector standard, a replacement, so to speak, for RIP, which is terribly incompetent as a enterprise routing protocol. RIP is simply not, I don't want to say it's not a serious routing protocol, but in complex enterprise environments, you're not running RIP. I'm sorry. So, but they took EIGRP and proposed it and submitted it. And they were basically told, thanks, but no thanks. We already have a distance vector routing protocol, and that's RIP. So Cisco, you can take EIGRP and go back to San Jose. And it was at that point where Cisco said, oh, okay, fine. Then we're not going to play with you guys, and we're not going to give out any of the information. For the longest time, this information has been sort of unknown, right? And I cannot recommend the reading of this highly enough. Again, the RFCs are gold in terms of information about a wide range of subjects, specifically for our interest, routing protocols, EIGRP, and OSPF. All right. So you've got a lot of other resources I've just guided you to. Those you can use to further your study. But the bottom line is OSPF is the interior gateway routing protocol in enterprise networks because it runs on Cisco, it runs on Huawei, it runs on HP, it runs on Juniper. So we can all talk and play together and everything's going to be great. With EIGRP, that is not going to happen. It's simply not going to happen, right? So I'm going to get off my soapbox now, but the last thing I'm going to say is if you want to be a serious network engineer, OSPF is a routing protocol that you need to invest time in order to understand and to know the semantics of and to be able to design, troubleshoot, support, so forth and so on. And it is a complex routing protocol, right? So it requires some work, but I'm telling you, it is one of the most rewarding things in the world when you're able to start manipulating and doing a stub network when all you need is a default route to get out. Or to do an NSSA when you don't need to see a whole bunch of different LSA types, right? So there's all of these things that you can do with OSPF. We're just scratching the surface here in this activity. Well, now I'm off my soapbox. And for those of you who are celebrating Christmas, let me wish you a Merry, Merry Christmas and a Merry Christmas Eve. This evening is when I'm doing this recording right now. It's about 7 o'clock on the East Coast here. I hope you guys, if you're traveling, be safe out there. Thank you so much for watching the video. And as I always like to say, I hope to see you in the next video.